Hello everyone, this is Rahmat Ali, PGT Physics from Indrapuram Public School, Indrapuram, Ghaziabad. In the previous session, you have learned about potential energy and the capacitors. Today we will discuss the chapter current electricity. Current electricity. It is the branch of physics which deals with the study of charges moving in a definite direction. Electric current. It is defined as the rate of flow of charges in a definite direction. If Q charges flow through a conductor in time t, then electric current I equals to Q upon T. Its SI unit is ampere, which is coulomb per second. Thermal velocity. At room temperature, all the free electrons are in random motion. Their velocity is called thermal velocity. Average thermal velocity equals to 0 as no current is available through conductor at room temperature. Drift velocity is defined as the average velocity attained by free electrons under an external field. Let's study the derivation for drift velocity. Let we have a conductor of length L, area of cross section A, having n electrons per unit volume. If U1, U2, U3, Un be the thermal velocity of n free electrons, then average thermal velocity U equals to U1 plus U2 plus U3 and so on Un divided by n. If an external field E is applied across the ends of the conductor, then force on each electron F is equal to E, the charge of electron multiplied by the electric field. If mass of each electron be m, then F equals to ma. Newton's second law gives us. Here A is the acceleration produced in each electron. So we get m into A is equals to small e, the charge, into capital E. Therefore, acceleration A equals to E, capital E, the field, divided by the mass. So velocity of ith particle, using the first equation of motion, Vi equals to Ui plus acceleration A into time t. So drift velocity equals to summation Uy plus A into Ti. So Vd equals to summation of Ui is 0 plus A into T. Here T is the relaxation time. Substituting the value of acceleration A, we get Vd is equals to small e, capital E, tau divided by m. Ohm's law. It states that current through any conductor is directly proportional to the potential difference available across the ends of the conductor, provided all the physical conditions like temperature, stress remains constant. In the diagram, let we have a conductor connected across the ends of a battery. If V be the potential difference across the ends of the conductor and I be the current through the conductor, then I is directly proportional to V. Therefore, we can say V is directly proportional to I. Putting a coefficient of proportionality R, we get V equals to I into R. Here R is called resistance. Its SI unit is ohm. So what is the cause of resistance? We know in a conductor we have large number of free electrons, hence we get large number of ions. Ions are much heavier than electrons. When an external field is applied across the ends of the conductor, then all the free electrons move in a given definite direction. As a result, there are collisions between the electrons and the ions present in the conductor. These collisions are responsible for the resistance. Relation between current and drift velocity. Let we have a conductor of length L, area of cross section A, having n number of free electrons per unit volume. So the total number of free electrons, capital N, will be equals to N A into L. So the total free charge Q equals to N into E. As a result, we get Q equals to N A L into E. If Vd be the drift velocity, then time taken by an electron to travel through the conductor, T equals to L upon Vd. So by definition, we get current I equals to Q upon T. Substituting the values, we get I equals to A N E V D. Deduction of Ohm's law. Using the concept of drift velocity, we can derive Ohm's law. As we know, I equals to A N E VD. Here VD is equals to small e capital E tau upon m. Substituting the values of VD, we get I equals to A N small e square, the charge, multiplied by the electric field, tau, the relaxation time, divided by the mass m. As we know, electric field E is equals to the potential gradient. So, E equals to V by L. Substituting the values of electric field, we get I equals to A N E square V tau divided by m into L. For a given conductor under constant physical conditions, A N E square tau upon m into L is constant. So, we get I is directly proportional to V. This is the Ohm's law. Here A N E square tau upon m into L is a constant, say R, which is referred as the resistance. Factors affecting the resistance of a conductor. Let's study some parameters which affect the resistance. Under constant physical conditions, we have seen that resistance is directly proportional to the length of the conductor and it is inversely proportional to the area of cross section. That means if we have a longer wire, then the resistance will be large, and if the finer wire, then we have high resistance. Combining these two equations, we get resistance is directly proportional to L upon A. Putting a constant of proportionality rho, we get R equals to rho into L upon A. Here, rho is called resistivity or the specific resistance. Its SI unit is ohm meter. As we know, R equals to A N E square tau upon m into L. So, rho will be equals to m upon n E square into tau. Specific resistance. As we have seen, R equals to rho, the specific resistance, L divided by A. If we want to define this specific resistance, then we have to take length L equals to 1 meter, area of cross section of the conductor A equals to 1 meter square, then we get rho equals to R ohm meter. So, resistivity is defined as the resistance offered by a conductor of unit length and unit area of cross section. Factors affecting the resistivity of a conductor. Resistivity. As we know, resistivity rho equals to m upon n E square into tau. So, here m and E are constant. So, we get resistivity is inversely proportional to n and tau. Effect of temperature on resistivity. For copper, we have seen that resistivity varies rapidly with the rise in temperature. That means in the beginning resistivity increases slowly, but if we increase temperature large, then resistivity increases. If we study the effect of temperature on the resistivity of alloys, then we have seen that with the high temperature resistivity remains almost constant. Whereas for semiconductors, we have seen that resistivity decreases with the rise in temperature. Following graphs represent the variation of resistivity with temperature. Carbon resistor. As we know, it is the time of electronics. Gadgets are reducing their size, so we need to reduce the size of resistors. So, we made resistors based on carbon. This diagram represents the carbon resistor. It is a band of 3 colors followed by a ring. In order to obtain the value of carbon resistor, we made a sequence of colors representing a certain number. Black is given 0, brown is given 1, red is given 2, orange is given 3, yellow is given 4, green 5, blue 6, violet 7, grey 8 and white 9. A carbon resistor has 3 bands of color followed by a ring. When we want to read the value of carbon resistor, then we move towards the ring. The first color gives us the first significant digit, the second color gives us the second significant digit, third color gives us the multiplier, and the ring gives us the tolerance. If we have a color pattern in a carbon resistor like red, orange, green, and the ring is of silver, then value of the resistance is 23 into 10 to the power 5 plus minus 10%. Here 10% is the tolerance represented by the silver. Tolerance is also represented by golden, silver and no color. If the ring is of golden color, then the tolerance will be 5%. If it is by silver, then 10%. And if there is no color on the ring, then the tolerance will be 20%. Grouping of resistors. We can combine resistors in two ways. One is the series combination and the second is parallel. In series combination, current passing through all the resistors is same, while the applied potential is divided among all the resistors. In parallel, the total current from the source is divided among all the resistors, whereas the applied voltage is same. Now, let's study the equivalent resistance of parallel combination. Let we have three resistors R1, R2 and R3 connected in parallel as shown in the diagram across a potential difference V. If current through resistor R1 is I1, through R2 is I2 and through R3 is I3, then according to Ohm's law, I1 is equals to V upon R1, I2 equals to V upon R2 and I3 will be V upon R3. According to the law of conservation of charges, we get I equals to I1 plus I2 plus I3. Substituting the values of I1, I2, I3, we get I equals to V upon R1 plus V upon R2 plus V upon R3. As V is common, so we get I equals to V into 1 upon R1 plus 1 upon R2 plus 1 upon R3. Now, if a single resistance Rp is connected across the given potential difference V such that the same current I is obtained across it, then according to Ohm's law, I equals to V upon Rp. As a result, we can say 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Here Rp is the equivalent resistance of the parallel combination. EMF of a cell. It is defined as the maximum potential difference across the ends of the cell when no current is drawn from the cell. Terminal potential difference. When a cell is in use, then it draws some current through the resistor. As a result, the potential difference across the cell is slightly less than the EMF of cell, and this potential difference across the terminals is known as terminal potential difference. Internal resistance. It is the resistance offered by the internal agents of the cell. Factors affecting the internal resistance of a cell. We have seen that the internal resistance of a cell, it depends upon the nature of electrolyte, electrodes, area of the electrodes dipped in the electrolyte, separation between the electrodes. Now, let's study the relation between terminal potential difference and EMF. If E is the EMF of a cell, V is the terminal potential difference across an external resistance capital R and small r be the internal resistance of the cell, then from the diagram we can say E minus V equals to I into R. Therefore, E minus I into R is equal to I into small r. Here I into capital R is the Ohm's law relation, which is the terminal potential difference across the external resistor. Always remember, while charging a cell, terminal potential difference of the cell is greater than the EMF of a cell. As a result, current flows in the reverse direction and the relation becomes V minus E equals to IR. Combination of cells. We can combine cells in series as well as in parallel combination. As we know, every cell has positive and negative terminal. In series, if we combine given number of cells, then total EMF of cells is added considering the polarity of the cells. That means, if we combine cells with positive, negative terminals of the cell, then the net EMF of the cells is added. If we have certain number of cells having EMF say E1, E2, E3 and so on En, then net EMF of the cells in the series combination will be E equals to E1 plus E2 plus E3 and so on En. If all the cells are identical, say n cells are identical, then net EMF will be equals to n times the EMF of the single cell. Now, if we consider n identical cells of EMF E are connected with the positive and negative polarities and m similar cells are connected with the reverse polarity, then net EMF of the cells will be equals to n minus m times the EMF of the cell. As every cell offers some internal resistance, if let us say it is R, then the resistance of all the cells is added. As a result, we get net EMF of the cell to be n minus m times E, and net internal resistance of the cell will be n plus m times R. If we combine cells in parallel combination, then the EMF of the cell remains same, that is E if all the cells are identical, and the net internal resistance 1 upon Rp is equal to n times 1 upon R. Here small r is the resistance of the cell offered by its internal agents. In this chapter, we have studied the drift velocity, Ohm's law, resistance, resistivity, combination of cells, and in the next session we will study Kirchhoff rules, meter bridge, Wheatstone bridge, potentiometer, and certain applications of potentiometer. I hope you enjoyed the session. Thank you for watching.